Sorry, thank you. Let me see if this allows me to work a little bit more here. Or maybe not. Okay. Hi, how's it going?
Good. How about yourself?
I'll bet you, I'm guessing that I just got, Peyton, did you get into the, get into the class, Peyton?
Yeah, I did. I figured it out.
Okay. All right. I tried for some reason, I tried just a moment ago to start the class and it was waiting for the host of the meeting to start the class, which is me. So I started it, but it wasn't allowing me to start it anyway. So I had to restart it. So bear with me if it takes me a minute every once in a while to get in. First, are there any questions or concerns?
Chapter 2, practice and quiz. Are those still going to be due tomorrow?
They're
or-
extended. If
Okay.
you go back and look again and see if they're extended because they should be.
Okay.
Bear with me and I'll make sure right now. Actually, that's not what I want. Okay, go see her so you don't cause chaos up here. Go get her. So if you look here, it's 22nd. No, it should be extended. The smart book assignment is still due. But the practice, yeah, it should be extended out. 1 second here. I'm going to do both of them. Give me 1 moment here. Can you mute yourself?
Oh, me? I'm sorry.
No, it's okay. I can hear what's going on in the background.
My dog's barking.
I understand that kind of thing.
Oh, wait. Okay, hold on.
Chapter 2 practice. I thought I extended it out. Maybe I did it and I did it for another thing and I didn't do it here. So I'm going to make them due on the 4th instead. Sorry.
Thank you. Yeah, I looked
Yeah.
like right before. I've been looking all week, but I looked like right before the class and it was still the 22nd. So I wasn't sure.
So I did the chapter 2 quiz. I just didn't do the chapter 2 practice. So let me do that and they'll let me do this one too. So I think I've kind of decided this, the first almost half of this PowerPoint has a lot, is the material's very abstract. and this, and once we get through the first half, things tend to move faster. So we're a little behind, but it will make up for it, because this is probably one of the more difficult chapters we're going to have all semester. I'm trying to remember if one of our chapters is more difficult than this. I don't think so. I think we were probably, all right, now I have to go back and look. 54. Which is not that far. Not that.
We ended on pH, like we just got through pH and like the algorithm.
So we were about right.
So my slide is showing like 60s, 60s something.
We were that far.
Yes.
Yeah.
I thought we were at 54, but we were actually we were up here.
Yeah, the last thing I have written down for notes was the pH.
So let me, so obviously my notes here are, you know what? I know why. So we were right here, correct? Approximately.
Yeah, approximately. We
Okay.
just did the acids and bases.
All right, now I remember. I can see where my error was. Okay. Well, I'm glad we're this far ahead. So strong and weak acids. So the major thing that you want to see here is strong acids, they dissociate completely. If I put hydrochloric acid into into water, give me 1 second here. I put hydrochloric acid into water. I put it into water. Actually, let me erase that part. Put it into water. It's going to immediately disassociate into hydrogen ions plus a chloride anion. It's going to do that every time. And in this reaction, this is a strong acid. So this reaction is irreversible. It will not go back in the opposite direction. It's always going to go in the forward reaction, and I can't move it back in this direction. So rather than have double arrows here, I get rid of one of these. This reaction is always a forward reaction. It will not go back in this direction. This is what we call a strong acid. A weak acid, and I don't know the exact structure right off the top of my head, but acetic acid, let's do this. Let's type for a minute here. Acetic acid is a weak acid. It will give up its hydrogens a little bit because that's what an acid does, but it's not going to do it to the same extent that hydrochloric acid will. It will give up some of the hydrogen ions, but not all of them. Another example of a weak acid is carbonic acid. Depending on the situation, it will give up hydrogen ions or it won't. And we'll talk a lot about this one here in a few minutes. So strong acids dissociate completely and irreversibly. Weak acids dissociate a little bit. They'll give up some of their hydrogen ions, but they won't give them up all the way. They won't give up all of them. Not all of the acid will immediately break down, only some of it. Bases are the same way. They can, in the strong bases, will quickly and irreversibly bind up hydrogen ions. And weak bases, in contrast, will bind up some of the hydrogen ions, but leave a lot of them not bound up. And they can release those hydrogen ions too, if they want. It's just not, so strong acids give up completely their hydrogen ions. Weak acids give up some, and they can do it in a reversible reaction, or they can take them back because they become bases at that point. With this in mind, and I know we had this slide before, but I'm putting it down here. I shifted it around once. I thought it would flow better if I put it down here. So water ionization results in the formation of an acid and a base. Two water molecules in solution. One of them takes the hydrogen ion from the other one. And the result is that we have an acid that can give up that hydrogen ion again, and a strong base, which will easily accept it back. That's why we call this an ionization, because the hydrogen that takes on, the water that takes on the hydrogen ion gets a positive charge. The base that loses the hydrogen ion gets a negative charge. So they both become ions. They both take on a charge. In pure water, the concentration of the hydronium ion and the hydroxide ion are equal. And therefore, the pH of the solution is neutral, 7. The amount of this equals the amount of this. Buffers are combinations of weak acids and weak bases that carefully regulate the homeostasis of the pH. They resist large changes in pH by releasing hydrogen ions. So they're a combination of a weak acid and a weak base. So if there is a drop in pH, the base will, meaning things become more acidic, the weak base will start absorbing the hydrogen ions. If there's an increase in pH, and we need to make it more acidic. Remember how pH is the opposite. The higher the pH number, the more basic the solution is. The lower the pH number, the more acidic the solution is. And if it's more acidic, it has more hydrogen ions in it. So this combination of this weak acid and this weak buffer, the weak acid will give up hydrogen ions to resist a change, and the weak base will take up hydrogen ions to resist a change. That's what makes it a buffer. Is there's two, there's a weak acid and a weak base. Buffers will convert strong acids or strong bases into weak acids and weak bases by removing or adding excess hydrogen ions. Any questions first? Buffer systems maintain constant pH values in different parts of the body because they're reversible reactions. I told you I typed in on the whiteboard carbonic acid here. This carbonic acid bicarbonate buffer system is the primary buffer that acts in the blood. We have a weak acid and a weak base. If the blood becomes too basic, this acid will dissociate and release more hydrogen ions into the solution, lowering the pH by making it more acidic. If the solution becomes too acidic, this bicarbonate will start absorbing the hydrogen ions to make it more basic. So the carbonic acid acts as a weak acid, donating hydrogen ions if the solution becomes too basic, giving them up. The bicarbonate acts as a weak base by binding up the free hydrogen ions if things become too acidic. So it's a balancing act. The reaction doesn't have to go one way or the other all the time. The direction of the reaction depends on the pH of the blood or any solution. A substance that is very acidic may have a pH of 1 or 2. This means that the acidic substance is what?
Is it D?
Yes, isn't it D?
You guys are smart. My first class that I have today was kind of a nightmare. So you guys are very, very smart. How did you know that?
Because we just talked about how it removes hydrogen ions if it's too acidic.
Right. And so if you remember, pH is equal or is approximate to the inverse of the hydrogen ion concentration? So as the hydrogen ion concentration goes up, the pH value actually is going to go down. It's going to keep going down. That's why a solution with a pH of that's 1 or 2 has a high hydrogen ion concentration. Kind of counterintuitive, but it's the way it is. You guys are very smart. You're already making my day a lot better. A buffer will release hydrogen ions. Remember that it's a combination of a weak acid and a weak base. If the blood pH does what?
I'm sorry, if it falls to
Yeah.
become acidic. B.
Why do you actually go back? What would you say the answer is? Tell me again.
Well, doesn't a buffer help with the acid, like rising acid?
It can go both ways. It works both ways. So if it becomes more basic and let's say that the pH drop becomes 8 when we should have it at 7.4, which is what blood is, it's gonna release hydrogen ions to make it more acidic. If the pH becomes like 7.2 or 7, it's going to increase the hydrogen ion concentration. Excuse me, it's going to bind up the hydrogen ions to make it more basic, make it back to being 7.4 where it should be. So depending on what the pH is at that any given moment, it's going to either bind up the hydrogen ions or release them. If the pH becomes more basic, which means that there's less hydrogen ions, the buffer is going to increase the hydrogen ion concentration in the blood. It's a balancing act all the time. We want to keep the pH at a 7.4. If it gets to be 7.2, we're going to bind up some of the hydrogen ions to bring it back to 7.4. If it becomes 7.6, we're going to release some hydrogen ions to bring it back to 7.4. Is that clear, kind of?
Yes.
So a substance that dissociates into one or more hydrogen ions and one or more anions is what?
Is it a strong acid?
It's an acid. Yeah, it's a strong acid or an acid. A substance that dissociates into cations and anions is what? Neither of which is a cation is a hydrogen ion or a hydroxide ion. Is what?
Is it a base?
No. Think back. If it's not giving up hydrogen ions, It's not producing hydrogen ions, and it's not producing hydroxide ions. Is it an acid or a base? What do you remember from what we studied maybe last week or even the week before that produced cations and anions?
I'm just gonna take a guess. Was it, I have written down ionic bonds.
I think you're right, but a cation and anion is something that is a salt. When you put it into water, it dissociates into cations and anions. And if neither of those cations or anions or a hydrogen ion or a hydroxide ion, it has to be a salt. That's the distinction. So you're right. Define a proton acceptor?
A-
What? Go ahead.
A base.
You're right, it's a base. What's the measure of the hydrogen ion concentration? What would measure that?
Is that pH?
That's pH, right? Good job, Kevin. What's the hydrogen ion donor?
Acid.
Would that be the acid?
Acid?
You're right, that's an acid. A chemical compound that maintains pH by converting strong acids or bases into weak ones is what?
A buffer?
A buffer, good job. So on to some easier stuff for a minute here.
Thank God.
I understand a little bit.
Can I just ask one question just so
Go
like
for
my
it.
my head's on right?
Go
So
for
back to the question where it said like buffers will release hydrogen ions if the blood pH falls. So
Yeah.
releasing the hydrogen ions, if I'm right, it brings back up the pH from where it is, or it drops down to where the pH
gonna
is.
drop it.
Okay.
Because it's gonna drop it because the pH value is actually the inverse of the hydrogen ion concentration.
Okay. And then the binding will bring it up, correct?
Yes,
Okay.
because if the pH goes up, the amount of free hydrogen ions in the solution has gone down.
Okay. Got it. Thank you.
And let me tell you, that is probably one of the more difficult concepts to keep straight in your head.
Yeah.
And so keep working on it because you have a grasp on it. So on to something a little easier. Energy is the capacity to do work. It can exist in two forms. So these are work capacities, with each type of form being easily transformed into the other. A potential energy is stored energy. So this is inactive energy that has the potential to do work, but is not presently doing it. So an example of this is the food in your fridge. It's a potential energy source. We're storing it, but we're not using it to create energy at that moment. it's a potential energy source, but we're not using it at that moment. It's an energy source that we're not using at that moment. Kinetic energy is you breaking down that food in your body and digesting it, metabolizing it. So kinetic energy is energy in motion. Performs work by moving objects. Different types of energy or different forms of it. We have chemical energy. Anytime that you have a chemical bond, that is a potential energy source. When we break those bonds, we release energy. That's kinetic energy. When the bond is present and it's not broken, that's a potential energy source. So if you break a bond, that, for example, ATP here, we have 3 phosphates here. Very high reactivity, that second bond right here. If we break it, we release energy. Also, we get a phosphate ion and we also release energy. If we take adenosine diphosphate, which is 2 phosphate groups, and we add a phosphate group to it, we have to absorb a certain amount of energy. We'll talk about that, talk more in detail about that here in a moment, to make it back into this. But this bond right here, anytime you see a bond like this, this is a form of potential energy that we can use if we break that bond. When we break it, that's a kinetic energy. Electrical energy is the movement of charged particles or electrical currents being generated when those charged particles move. If you think brand new battery, any battery, your Duracell battery, a battery works because there's a flow of charge from one area to another area in the battery. If the battery is not dead and still usable, the whole reason it's a potential energy source is because there is a separation of charge between 2 parts of the battery. Once we activate the battery, we start a flow of current that moves from one part of the battery to the other part of the battery. And we can use that to do other work. So the potential energy source is the battery with the separation of charge. The flow of current is the kinetic energy, because that's the energy in motion. That it is the same way, and we'll talk a lot about this when we talk about the nervous system. This is the same way that the neurons work. There's a stored energy source in the separation and charge across the membrane. We can allow the current to start to flow across the membrane, and that is an energy source that we can use to do other things. Mechanical energy is energy that's directly involved in moving matter. For example, your biceps contract to flex your elbow joint. Your triceps contract to extend your elbow joint. Radiant or electromagnetic waves are like light waves or electron wavelengths. if you've talked about microscopes in lab yet. Electron wavelengths are a form of energy. Light waves are a form of energy. X-rays are a form of energy. Radioactivity is a form of energy. Any questions so far? So chemical reactions occur whenever chemical bonds are formed, rearranged, or broken. Chemical reactions can be written as chemical equations, where the reactants are the substances reacting in a chemical reaction, and they're typically written on the left side of the equation, right here. And the products are the substances being produced at the end of the reaction, and they're typically written on the right side of the reaction. So in this case, in the production of methane, 4 hydrogen atoms are connected to 1 carbon atom. These are our reactants. The product that's produced is methane. We have reactions that are reversible, which means that they can go backwards and forwards under different circumstances. They can either go from left to right or right to left. The law of mass action says that whether the reaction goes from left to right, the forward reaction, or whether the reaction goes from right to left, the backward reaction, depends on the relative abundance of substances on either side of the equation. Whether if the more abundant substance is the substances on the left, the reaction is going to go from left to right. If the abundant substances are greater on the right side, the reaction is going to go from right to left. To reach equilibrium is when the ratio of the products and the reactants being formed on both sides is stable. So when the rate of products being formed and the rate of reactants being formed are equal, the reaction is in equilibrium. This type of reaction is quite common. We'll discuss it at length in future chapters. All reactions are theoretically reversible, so they can all, theoretically, they should both be, you should be able to push it forward and push it backward. If the forward reaction dominates, the product will accumulate. When neither the forward or the reverse reaction dominate, the reaction is in a state of chemical equilibrium, and there's no net changes in the amount of reactants being produced or the amounts of product being produced. In most biological reactions, the forward reaction is going to dominate. And most biological reactions are assumed to be irreversible. Once they occur, you can't push them back in the opposite direction. So once the reactants react and form the products can't become the reactants again. These reactions that are irreversible will are you release energy. This is what we call exergonic. I'm gonna introduce some terms here. So exer means energy, means, let me say it here. Exiting or releasing. Enter means entering or requiring. Gonic means energy. So a reaction that's exergonic means that energy is leaving that reaction. It's going to be one of the products, or it's releasing energy. Endergonic means that that reaction requires energy, or energy is entering the reaction and into the products. Put it another way. Exergonic means that the only way the products are being produced is by the release of energy. Release of energy in addition to the products, with the formation of products. Endergonic is the absorption of energy by the products, or when the products are made. So exergonic is the release of energy with the formation of products. Endergonic is the absorption of energy when the products are made. So an exergonic reaction, glucose being broken down, this reaction also requires oxygen, is going to result in energy being released in addition to carbon dioxide and water being formed. It's an exergonic reaction. Anabolic reactions require energy, which means that these are always endergonic reactions. Anabolic reactions are defined as chemical reactions that synthesize smaller molecules into larger molecules. And if you're going to synthesize things, you're going to create bonds. And remember, each one of those bonds is a form of energy. So we have to put energy into it to make these bonds. A catabolic reaction produces energy or releases energy. These are always exergonic reactions, where larger molecules are being broken down into smaller molecules, always releasing energy. The way that I remember this is I think about cannibalism, kind of a graphic term, but cannibalism. Somebody tell me what cannibalism is.
When you eat people, or
When you
Humans.
eat, when people eat people. Yes, when people eat people. So I think of cannibalism as being catabolism, which is the breakdown of myself. That's the way I remember it. And because when I think of anabolic, that usually has a negative, in my head, it can be like a negative thing. That's not the case here. It's the opposite. So I think if I think catabolism and cannibalism, it's the breaking down. And anabolic is the building up. Synthesis or combination reactions involve bond formation. So anytime and between smaller molecules or atoms. And anytime that we're having bond formation, that means that energy has to be required for this reaction to occur. So synthesis reactions are the basis of anabolic reactions or any anabolic activities in the cell. Decomposition reactions are when molecules are being broken down into smaller molecules or atoms. This is the basis of catabolic reactions in the body. Remember, this is always energy releasing. If we're breaking down bonds, we're releasing energy. If we're forming bonds, we're requiring it to build bonds, those bonds that we make. Exchange or displacement reactions involve both the decomposition, the breaking down, and the synthesis formation of bonds. So parts of the reactant molecules are exchanging themselves. So it involves the breaking down and the synthesis of bonds in the same reaction. Oxidation reactions involve the exchange of electrons. You guys, when have you seen the exchange of electrons? We've seen this before. When did we see it?
Ionic bonds.
Yes, exactly. You guys are so smart. Ionic bonds. Because we have to give up an electron and something else takes it, right? So one atom gives them up, loses them, one of them gains it. When we're dealing with organic molecules, which we'll talk about here in a moment, it's more that we're losing or gaining hydrogen atoms. So instead of electrons, we're losing hydrogens, and another molecule is gaining the hydrogens. So oxidation is the loss of electrons or hydrogens. Molecule that gets oxidized loses electrons or hydrogens. A molecule that gains electrons or hydrogens is reduced. In one reaction, one molecule loses electrons and gives it to the other reactant, which gains electrons. In the case of hydrogen, or when we're working with hydrogens, remember this is essentially, it's just instead of using electrons, we're using hydrogens. One loses hydrogens, one of the reactants loses hydrogens, gets oxidized, and the other one gains those hydrogens and becomes reduced. Now the mnemonic, because this is kind of like pH, you don't think of getting reduced as being a gain. The mnemonic for remembering this that I use is this. Leo Gosger. Loss of electrons means oxidation. Leo. Gain of electrons means reduction. I add one more thing in here because we know that we're going to be dealing a lot with organic molecules, and therefore it's not so much going to only be electrons, it's going to be hydrogens or hydrogens. And the gain of hydrogens is going to be a reduction. So loss of electrons is an oxidation, or loss of hydrogens is an oxidation. The gain of electrons is a reduction, or the gain of hydrogens is a reduction. So all chemical bonds store energy. Remember, anytime you're looking at a chemical bond, it's a form of potential energy. And all reactions either involve the absorption or the release of energy. Reactions that release energy are exergonic. Reactions that absorb or invest the energy are endergonic. If one reaction releases energy and another reaction requires or absorbs the energy, we can couple these together. A reaction, and I'm going to switch these numbers around. So this is going to be reactant 1, and this is going to be product 1. This is going to be product 2. This is going to be reactant 2. So I have an exergonic reaction, meaning I'm breaking a bond. Or I'm oxidizing on a reactant, which is also an exergonic reaction. We'll see that in a moment. So reactant 1 becomes product 1 and releases energy. It's one of the things that comes every time that this reactant 1 becomes product 1. It releases energy, and this energy can be used to convert reactant 2 into product 2. So I can couple these together. The energy released from this reaction can then be used to drive this reaction. So summary of chemical reactions. Oxidation. So three different types of oxidation reactions. And remember, catabolic and decomposition reactions are essentially the same things. Things are being broken down into smaller items. And if we lose an electron or a hydrogen atom, that's an oxidation, that's also an exergonic reaction. We have to pull an electron from something. And that requires energy. Actually, that releases energy. I'm so sorry. That releases energy. If we gain an electron, that's an endergonic reaction. So that's a reduction reaction. And also the other two endergonic reactions are anabolic and synthesis reactions, which are the same thing. If it helps you to remember, catabolic reactions are the sum of all of the decomposition reactions in the body. Anabolic reactions are the sum of all the synthesis reactions in the body. We're not going to talk a lot about digestion this semester. I think you'll see it a lot more next semester. But when someone is losing more weight than they are bringing it in, their body is in a state of catabolism or catabolism. I think you've probably seen my monster of a cat every once in a while. He's the one who likes to mess with my keyboard. Come here, buddy. Show your face. Come here. Show your face. Show your face. So this is Leo, my little monster. Okay, show your face. He's a little bit of a firecracker. And I wouldn't give him up for the world, but he's a little bit of a firecracker. And the reason I'm bringing him up here is about a year and a half, he became very catabolic. What that meant is that even though he was eating all the time, he was showing all the signs of being anorexic. He was metabolizing away all his muscles for energy. And if you see him now, you wouldn't believe that because he's 14 years old. He just turned 14 in June. And so about the time that he was almost 13 years old, he stopped absorbing the food he was eating. The gastroenteritis, so his intestinal tract became very inflamed. And the result was that he wasn't absorbing anything he was eating. And so to maintain his life and maintain his vitality, his body was metabolizing away all his muscles. And so he went from being 9.5 pounds to 6.5 pounds within probably about, I would guess, because his mama, me, is a little slow on the uptake sometimes, he probably happened over a period of about 1.5 months, maybe 2 months. And one day I looked at him and thought, he doesn't look well. He doesn't look well at all. And I took him into a vet, and long story made short, $2,000 later, we realized that the small intestines his small intestines had become very the lining that is supposed to be involved in absorption had become very, had thickened, which meant that all the nutrients that are supposed to diffuse from your small intestines into your bloodstream was not occurring. And so everything he was eating was just coming out the other end. And he wasn't absorbing anything. And talking with my mom about that, she's my retired nurse practitioner. She said that's a state of catabolism, where the amount of catabolic reactions are far exceeding the amount of anabolic reactions. And so now he's on a special diet with food that's easily absorbable. And he's at a very happy 14 pounds. But so that the whole reason I'm telling you that is because think of this catabolism is the sum of all of the reactions of your body that are involved breaking down large molecules into smaller molecules. And the anabolic reactions is a sum of all of the building reactions of your body, building smaller molecules into larger molecules, synthesis. Factors that influence reaction rates, temperature. If I increase the temperature of a reaction, I'm adding energy to that reaction, which is going to increase the reaction rate. If bear with me here. Do we get out at 145? Is that right?
Yes, I
Okay.
believe so.
So the concentration, if I increase the concentration of my reactants or increase the amount of molecules reacting, I'm going to get more react product being formed. Remember, the reactants are on the left side, products are on the right side of the reaction. So if I increase by that law of mass action, if I increase the number of reactants I have, I'm going to get more products being produced. Particles, if I make things smaller, they tend to move faster. And that allows for more reactions to be produced and for more product to be produced. I can also introduce enzymes, cofactors, and coenzymes that will increase the reaction rates by being intermediates in the reaction that won't be chemically changed by the reaction, but just work to increase the reaction. Shifting gears a little bit, inorganic versus organic compounds. Inorganic compounds are simple structures that are small size with few atoms and are formed either through ionic bonds or covalent bonds. Some examples are water, sodium chloride, and carbon dioxide. Carbon-based atoms are organic compounds. For any compound to be organic, it must contain carbon and hydrogen. Organic compounds are chains of carbon atoms that can also contain nitrogen, sulfur, phosphate, and oxygen. They're larger sized, they're more complex structures, they have covalent, and they're made only by covalent bonds. And some examples are macromolecules and polymers. So why is the basis of organic compounds carbon? Why isn't it potassium? Why isn't it zinc? Why isn't it chlorine? The reason is is because carbon is an electroneutral atom. Talked about electronegative and electropositive. Carbon is electroneutral, which means that it never loses its electrons and it never gains electrons. It only shares them, never gets ionized. It only shares them. Also, carbon has 4 valence electrons and bonds with other atoms so that it can be provided with the 4 more electrons to fill its valence shell. It's very versatile for that reason. So remember, if it has 4 valence electrons, it wants to have 8. So it's going to make easily 4 more bonds with atoms to fill that valence shell. Very versatile, and thus can form large molecules with very elaborate shapes. So it never loses its electrons, only shares them. What elements must an organic compound contain?
Car Did you say organic compound?
Uh-huh.
They contain carbon.
What else?
Mhm.
What else do they have to contain? Because carbon dioxide is not an organic molecule.
They have electrons.
Hydrogen.
They have to contain hydrogen. So they have to contain carbon and hydrogen. What types of bonds does it form with other atoms, carbon?
Complex.
How about we say, Kevin, how about instead of saying complex, we say covalent? Does that sound good?
That sounds better.
Okay. So because you're right. I'll bet you that was what you were gonna say. And it just came out differently. I understand that more than I can say. So because carbon will never give up electrons completely and it never loses electrons completely. It's only going to share them. How many bonds is carbon capable of making?
Is it 4?
It's 4. Because it's going to share to get an additional 4 electrons in its valence shell because it has 4. So it wants 8. What types of structures can be made with carbon? All sorts of structures. All organic molecules. So carbon skeletons, and a carbon skeleton is defined as a molecule that contains just carbon and hydrogen. Carbon skeletons can vary in length, can be long chains, they can be short chains, they can have double bonds, or they can be single bonds. They can branch, and they can form rings. My question for you is, are these carbon skeletons, all of these carbon skeletons here, are they polar or are they non-polar? Are they polar or are they non-polar? What does a molecule have to be a polar molecule?
Is it non-polar? Because it's all, everything's equal and they're sharing electrons.
Right, and the way that you know that is there's no electronegative atom in there, in those structures. So that's the way Caitlin knows that, is because there's no non-equal sharing because there's no electronegative atom there. Now, in the last 2 minutes, I'm going to introduce one more. So we add functional groups or appendages on carbon skeletons to change their chemical reactivity, because usually most non-polar atoms are not reactive. They don't do anything. We have to, if we put some polarity to it, then it becomes reactive. So we have to add what's called functional groups to these carbon skeletons. So these small clusters of atoms are attached to a carbon skeleton, usually represented by R on a carbon skeleton. Actually, the carbon skeleton is represented by an R. And their presence gives properties to the organic molecules, gives them chemical properties to which they're attached. So we have a hydroxyl, which is an OH. We have a methyl, which is actually non-polar, which has a carbon and 3 hydrogens. One carbon with an oxygen and an oxygen and an oxygen and a hydrogen. Nitrogen that has 2 hydrogens attached to it, and a phosphate with 4 oxygens and 2 hydrogens. On that note, so non-polar, let me just summarize really quickly. Non-polar molecules are they don't react overall. If we add some polarity to it, that's when we add some excitement to it and it starts to react. Things that don't react also are kind of exciting, but not in comparison to when we get things to react. Therefore, to make something reactive, we have to add a functional group to a carbon skeleton. And that's when they start to show chemical properties that are reactive. And we'll talk about those functional groups that are coming up on this next slide when we come back to this same point on Thursday. Are there any questions? I know we're now over past 1:45, but are there any questions?
No.
Okay. I will see you guys on Thursday, all right?
Thank you.
Thank you for making my day better. I was about ready to have
Bye-bye.
a meltdown right before class started.
Bye.
You're welcome.
All right, bye-bye.
Bye-bye.
Okay.